So I'll get started. I'm going to give a workshop on numerical DEs in Maple today. And I've got a lot of material that we can cover, or if I have questions, we can always expand on something, add information, try other things. You've all been sent a link in the chat to this very worksheet that I'm going to be using to show. So for one, you can follow along in the worksheet if you like. You can use the worksheet as a starting point to try other things, change things around, modify something to be one of your problems. If you run into any issues or don't understand something, by all means, type something into the chat and somebody will either answer the question or direct it to me, and I can answer it for everyone. Okay. So we might as well, it looks like people are still joining. Oh, yeah, by the way, I'm Alan Whitcoff, fellow at Maplesoft. So I'm gonna get started now. So I'm just gonna start with an overview of the type of stuff you can do with numerical DEs in Maple. So we have tools for visualizing numerical computing numerical solutions of systems of differential equations for regular initial value problems, boundary value problems, delay differential equations, differential algebraic equations, and partial differential equations. So for any of the univariate stuff, initial value problems, boundary value problems, and the like, dsolve is the command you want to use, and the numeric option gives you the numeric solution as opposed to an attempt at an exact. So very simple example, harmonic oscillator, initial conditions y at 0 is 1 and y prime at 0 is 0. We just call dsolve with this system and the numeric option, and it gives us a solution, and we can use this to compute a value at any point we like. Just request the value. Boundary value problems, well, that's just like an initial value problem, but now you're specifying conditions at more than one independent variable point. In this case, I'm specifying a value at 0 and at 1 for this differential equation here. Again, just throw it into dsolve. You get a solution procedure, and you can ask for a value at a point. This this is a recap of a lot of the stuff from yesterday, but ODE plots can give you a plot of your solution. So we try to make everything as easy to use as possible. So if you just call it with the solution, it detects, well, yeah, this was a boundary value problem over 0 to 1, so it chooses the right range for the independent variable. Leading nonlinear ODE. In this case, the highest derivative in the equation is not linear, simply a quadratic. And for those type of initial value problems, this can be treated as a DAE. And we can obtain a solution for these as well, pretty straightforwardly. And you'll notice we've provided an extra initial condition, and we need that because of the arbitrariness of the square. Y prime can be positive or negative, and give the same value out of y prime squared. Okay. We also support more complicated DAEs, of course, higher index. And a simple delay equation with a delay of 1. Okay, we can just, again, pass it into dsolve. We can get a plot. And the plot's a bit interesting because you can see that for the first second, it looks pretty constant, a nice constant slope, which is a reflection of the fact that the initial condition, y at 0 is 0, is being assumed for all prior times as well. And then it starts changing more smoothly. Okay, so PDEs are a little limited at this point to one space, one time PDEs. And the PDE solvers that we have, well, the PDE methods that get used was always intended on the initial design to be using it in a course because we've got a lot of the standard techniques that get taught in courses available. And there's a help page to describe all the basic techniques like Lax-Friedrichs leapfrog, my apologies, and de Fort-Frankel. For a standard PDE, you don't need to specify the methods. You just pass in your PDE problem. In this case, we've got the PDE and the conditions specified separate, initial and boundary conditions. And instead of a procedure, we now get a solution module, just because it was more convenient to do this way, because then you could get direct access to 3D plotting directly through the module itself. So the module form, we can ask for the value for t equals 1, and it gives us a procedure that looks a lot like the one we got from dsolve. So a single variable procedure that we can use to evaluate. And we could have used the procedure itself, or we could just simply ask for a plot directly from the returned module. The returned module also produces animations directly. So we can ask for an animation from t is 0 to 1. And it just gives us an animation automatically. And we can also get a plot, a 3D plot of the solution as a function of time and space. So that's just an outline of the facilities that are available in Maple at this time. So I'm going to get into a bit more detail on some of these. So for IVP specifically, there are a lot of options, and I'm going to describe also the interactive features of initial value problems, and not the interactive feature I showed yesterday, which was the dsolve interactive, but rather the ones that you can use from command line. So we have high accuracy techniques like Taylor series, and I'm going to briefly demonstrate how fast that is. We have stiff solvers like Rosenbrock and LSODE. We have handling events. These are discrete actions that happen in the course of integration. You can reinitialize, you can run a state machine. And like I said, discrete variable state machines is kind of tied into event handling. A lot of these have links. If you've got the worksheet and you click on one of these links, it'll just take you right to the help page that describes these in explicit detail. The event handling page also describes discrete variables and state machines. Parameters, we can support parameterized problems and do the computation on request. We have the compile option, and it's quite a strong thing to be able to do if you can combine the compile option with parameters. So you can parameterize a problem and have a compiled code running under the hood that very rapidly gives you different solutions for different values of the parameters. You set the parameters, obtain a solution, and so on. This is good for parameter optimization, which you'll see later. And as I mentioned, the interactive design. We're going to show a bit about that. So high precision. This Maple, of course, works with arbitrary digits. You just specify a digit setting, and that's the precision it will work in. For this problem, I'm going to set digits to 30, and I'm going to try and solve basically just the harmonic oscillator. And in fact, it's a signed solution. And I'm going to specify that I want an absolute error and relative error of no more than 1e minus 25, and I'm going to try and use a high order RK pair, Dvorak 7/8. So we're going to see how long it takes to compute this out to 10 with roughly about 25 digits of precision. And it's not fast, even for a order 7/8 pair. So and we can compare and make sure at least we're getting the right solution. And in fact, it does match up. And we can ask, okay, how many function evaluations did we need to do? And it was quite a few, 42,000. If we could do the same with Taylor series, which is designed for higher accuracy, and it's quite a bit quicker and gives quite similar precision. In fact, in this case, a little bit better, but you've only specified a tolerance of 1e minus 25. So you can see the time difference is quite substantial. And Taylor series is what you want to use if you have high accuracy solution requirements. Briefly, stiff problems. This is a standard stiff problem. We're going to attempt to attack it with just the standard RKF4-5 technique, and we can see that in order to compute the solution out to t equals 10, took us 20,000, roughly about 20,000 function evaluations. The same thing with the stiff method, and you can just simply specify stiff equals true in the call to desolve. And that computation only did 588 right-hand side evaluations. So it's using a stiff method for a stiff problem is much more efficient always. Again, links to help pages on these. Okay. Events. Events take a bit of description. Okay. There are two parts to an event. There's the trigger, which is basically asking the question, when should the event occur? And then there's the action. What should we do when the event does occur? So standard triggers, expression passes through 0. So, and you can, expression passes through 0 when a condition is true. And this is great if you want to only fire an event under some circumstances. Expression goes outside a specified range. So if you have a problem where you know that value needs to be within a certain range and you want to stop and reassess what you're doing, if it goes outside that range, you can just specify the range and it'll stop when it goes outside. You can do a specific time value or a periodic value. For example, you can have something start at t equals 2 and trigger every half second after that. Okay, that's how you set up triggers. Action. The most obvious one is halt. Once you achieve this event, you may want to stop the simulation. You may want to execute a statement or multiple statements. You may want to run a state machine. Again, a state machine would be via statement or multiple statements, but in addition, for a state machine, you'd want discrete variables. And I'll show briefly how to do that here. So I'm going to define an event for a model, and I just have a simple model here, y prime equals y. And I'm going to say if we hit y equals 2, stop. And when we try to integrate out to 10, it tells us can't evaluate this solution for the right of this value and event 1 trigger to halt. And then gives us the solution value at that time. So we can see that, yeah, this did exactly what we asked it to do. At this time, y hit 2 and we stopped. We can do something different. We can say, well, instead of halting, let's reset the value of y back to 1 every time it hits 2. And we get this. So goes up to 2, reset, up to 2, reset. So this is like for those familiar with the terminology, this is a reinit. So we reinitialize the problem every time it hits a certain value. And I'm just going to modify this one slightly to show what you need to do to use a discrete variable. So we have exactly the same problem, but I'm adding something called num reset. And what I want to do is I want to count the number of times we had to do a reset. I declare that as a discrete variable here. And then I define the event with an action with 2 statements, reset y back to 1 and increment num reset by 1. So we run that and we can plot num reset and say, well, how many times have we reset? And we can see that it creates a staircase that, pretty much mirrors the behavior we saw in the plot. So if you run the simulation, there are a couple of interactive triggers or interactive features, like you can say, how many events fired? And when was the last time event one fired? So this is part of the interactivity. We'll see more on that later. And that's it for events for what I'm going to discuss here, but there's a lot of detail and other examples in the help pages. Parameters and compiling. Okay. Initial value problem solutions are done on request. So what you returned is a computation engine that you can use to ask for values, and the values get computed when you ask for them, unless they are already known or unless it's a repeat of a prior value. So, or I should say the very prior value. We can, in this case, set up a problem. This is just the simple harmonic oscillator again, but now we're adding a variable for the frequency. And we're going to also parameterize the initial slope of the solution. And we just declare parameters here, A and B, as our parameters, and ask for a solution, and we get this back. Okay. So if we try and compute a solution right away, it's not going to let us, because it's saying, well, hey, we've got A and B, we don't know what they are. You can ask what the parameters for problem are, and you can set them in this way. And now when we ask for a solution at 1, it's fine, and it's computed with those values. Okay. We can also obtain a plot, just using ODE plot, just as before, for the solution. So these were our parameter values. We can change them, and then we can see that, okay, once we change them, the solution procedure we're currently working with has now been modified so that it's using the new parameter values, and any computations performed will be at those parameter values. Okay, larger problems. This is where it gets more interesting. So if you have a very large problem, parameterization can be really handy, especially combined with compile. So I'm parameterized a problem here, but I'm not using compile. And I did essentially 100 calls with different values of the parameters, integrating out to 1,000, and it takes a certain amount of time. In this case, 0.84 seconds. This is a small problem. Larger problems, you'll see much larger times. So we'll do the same thing with compile now, and we can see it's significantly faster. Thing to keep in mind is this is a really simple function. I mean, the evaluations, when you do the right-hand side evaluation, are going to just be the square and a product to evaluate. So just compiling that part, the core engine, the actual integration engine, already compiled code. But now when it's compiled code using a compiled right-hand side prop, it's significantly faster. So this is going to be really handy for parameter searching and those type of things. So compile is really, really relevant here. Okay. Now, interactivity. What can we do? What can we do interactively with the procedure? You've seen a few up above. We can ask how many evaluations we had to do. We can ask how many events, how many times events have fired, when the last event is fired. We can ask what parameter values we're currently working with, or what the parameters of the problem are. But there are a lot more. We can ask what method was used to solve for the ODE. We can query and set the initial values used for the ODE. We can ask for the last value computed for the ODE. A lot of event control stuff as well. And array, you might have briefly seen in Jürgen's presentation yesterday, use of data array output. And I'll show that here too. So a few examples of this. I've got a pretty loaded example here. So it's got parameters using events, and I'm using a stiff solver and compiling. So this gives us our procedure back. We can ask, what's the method? And it tells us it use Rosenbrock. Current initial conditions, y at 0 is 0, y prime at 0 is b. Last value computed, well, we haven't called anything yet, so there's nothing. So now if we do an evaluation, wait, we haven't set the parameters. Okay, we'll set the parameters. Ah, and I see a question from, is it Nader Jant? He recently changed to using a compiler that is shipped with part of Maple. Are you working with 2025 or an earlier version of Maple? Compilation in early versions of Maple on Windows requires setting up MSVC, but that's no longer required at this time for newer versions of Maple. We have a variant of GCC that ships with Maple now. Okay, so compile in more recent versions of Maple will work right out of the box. So we request the value out at 100, we get a value. Now we ask for last. It tells us what the last value it computed was. We can clear the event. So we noticed that it actually halted when we asked for the value at 100 at 3.14. And again, this is one of the places where last is handy. We can clear the event to say, okay, let's clear that halt trigger and continue integration. And if we do the clear, and then we call it again, it runs until the next event occurs. And so on. We can clear that and ask for it again, and it goes until the next time the event occurs. This is really handy if you have an integration that you want to do where you're performing the integration and you want to be able to update or get the information at a very specific interval. You can set an event to halt and have it running in real time alongside some other computation if you need. Handy thing here. Explore. I want to integrate the parameter options with Explore. I'm not sure. I haven't used Explore that much. I'd have to look and get back to you on that. So somebody asked if one can integrate the parameters option with Explore. I don't think it currently is, but I'll take a look at that after and see. At the moment, the parameters option works with the interactive desolve. So parameters are automatically handled there, and that acts a bit like Explore, but it's not the actual Explore command. Continuing with this example, we can turn that event off entirely and just say disable it. And now what happens is it runs as though you'd never specified the event to begin with. You can again ask how many function evaluations. Now the new to Maple 2025 is the array feature. If you call with just array and nothing else, and I'm using the string array here because array is a reserved word, it's a command. It will tell you, okay, if you ask for array output, these are the columns you're going to get: t, y of t, y prime, a and b. And we include the parameters just so that one can't get confused about a data set. So now if we ask for array output, and this is a little bit of a tricky specification as described in the help, we're going to integrate out to 10, and we want 101 points. And this is the notation we currently use for that. So I chose 101 because it would give us nice, easy divisions of for 101 points out to 10, and we get the output here. And so this output can then be used as input to other things. It can be saved. And there's a question, when do you apply the command event dsend event disable? When you disable the event, it essentially just tells the integrator, turn the event off, but resume from start. So it's actually going to reintegrate from the beginning when you turn the event off at this time. Okay, so we've got this data. Now, if anybody attended Dave's plot structure stuff, you'll see that, it's often easy to just call plot with, simple data structures. And so I'm just extracting the result, all columns, or I should say all rows, columns 0 and 1. And I have to cast that into a matrix, because otherwise, if I just ask for 0, 1, it's indexed from 0 and it wants the 1 and 2. So if I can just call this simple command to directly display the plot without having to go through ODE plot or anything else. Okay. All right, so I'm gonna just briefly pause here if there are any questions on this section for interactivity, the parameters compile and such. Okay, I see a question. Is there a simple method to change the parameters in ODE on events? Okay, so the easiest way to do that, if you want a parameter to be changeable in an event, is to make it a discrete variable instead. So because technically speaking, if it's changing during the simulation, it's more of a variable than a parameter. So you can declare the variable as discrete, set the initial value to whatever you want to start it at, and then have the event assign a different value. So where was that example? Where's my discrete? Oh, that would be in events. Okay. Right. Okay, so what we're going to do is we're going to add in f of t here. Okay, and we're going to declare it. Okay, we're going to set an initial value. We'll start it at 1. And we're going to change this around to say, okay, when y of t is 2, instead of doing this, we're going to set f of t is 10. All right, let's make sure I've done that right. So we start off at a frequency of 1. We don't need num reset anymore because I've gotten rid of it. Okay, and there. Oh dear. Why was this? Not sure why it's discrete variables I've declared. Oh, sure, I was working with this once. Let me get back to you on this example. I'm not sure why this isn't working. This was. Kashka, can you make a note and I'll get back to the person? Thanks.
Will do. There's a couple more questions.
Okay, fire away.
Take a look at. So Arthur asks, using STET to compute times is all well and good. How about time to find parameters in the help facility? Is it substantial?
Using STET. not sure I understand the question. STET. Arthur, do you want to
Yes,
take yourself
maybe
off mute
Arthur,
and speak? That would be fine.
or if you could elaborate in the chat. In
Yeah,
the
either
meantime,
way.
David is asking, I am currently looking at events help page, and could you explain some of the options like to begin? I am also interested in conditional triggers. How do they work?
Okay, well, to begin to end all of those other things, they're related to state machine. So what you do is when you create a state machine, you define a discrete set of equations that run. What you can do is, and they'll run in exactly the order you specify them in the list. So when you say to begin, that basically means that once you hit this specific action that has a to begin, you bounce back to the very start of the set of discrete equations to evaluate. To end jumps you to the end. And basically, you have to think of things in terms of that framework. And for conditional triggers, let me find a good example here to start. For conditional triggers, you just define, I think there's an example in the help page, but you just have to define the condition combined with the trigger. Let me pull up the help. Let's see. Oh, no, that won't work because I'm sharing screen. Yeah. You just need to, there is, as I recall, an example on the help page that does a conditional trigger. But conditional trigger, I saw a presentation over the conference where there was a specific condition that needed to be met, was being met in two places, but only one of them was the one of interest. And you'd be able to set the conditional for that trigger so that only the one of interest would be specified. Okay, Arthur. So I see the actual time to solve the ODE is trivial compared to the time to find the word parameter in the help pages.
You hear me?
Yes, I do.
Okay. So my point is that when you want to do some research and you're solving a problem,
Yeah.
you start with the problem and then you have to look up how to use parameters. It's not obvious. In fact, it's a bit subtle.
Okay.
If you go to the help pages and look for parameter, you won't find it for quite a while. It's buried very, very deep, and you have to be very specific. And if you go to the desolve numeric page, you still have to dig deeper. Those things are not obvious. I think what you need is someone who's not familiar with Maple to try to solve problems. And then the difference between setting up parameters via the newer method rather than the old method of just using a procedure, while it's much, much better, it really does have to be explained and it
Okay.
has to be findable.
So perhaps a front facing desolved numeric parameters help page would be in order, and so that even searching just on parameters, you would see it.
Yes.
Okay. That's a suggestion that um, that I can definitely do. I will have that on my list. But
Okay.
yeah, it's we want people to be able to see this so that they can use it for sure.
And by the way, the explore function is fantastic, but it would be very nice if it could be integrated with solving ODEs.
Yeah, I can look at that. I'm not as like I said, I'm not as familiar with the Explorer, but I'll take a look.
Good, thank you.
Thank you.
And Alan, while you're at it, David also commented that maybe desolve events need some better examples.
Okay. All right. I will definitely also put that on the list. Yeah, it's a fine line between too many and too few, but I will definitely add several for the events, especially in context of, okay, let's make it easy to see exactly how to put a conditional on it. And probably, yeah, something better. But you can get really involved with state machines and the examples can become very long, very fast. But yeah, by all means, I'm happy to add examples. Yeah, good. Any further comments on that section? Okay, we'll move on to parameter optimization. Okay, I'm just giving a couple examples of parameter optimization. So we have a parameterized ODE here with y at 0 is 1, and our question is find A so that y at 1 is 2. So it's a pretty straightforward problem. So we just define our problem with the parameters. As always, I'm using compile is true. Now, this is a little tricky bit of code. So I'm going to define an objective function, okay, that takes in a parameter value and essentially uses this solution procedure directly, which I've declared as global because it's outside. And I call it and set the parameter, and then I just return the value of y at 1. So small bit of glue code, subtle, but it's not that difficult when you get the hang of it. And I can say, well, okay, if I now call this with 1/2, this sets the parameter to half, does the integration out to 1, gives me the value at 1. And there it is. Now that you've set this up to be a simple single input, single output type process, you can now call it with fsolve directly. So you can say fsolve objective of x is 2 and get a value. We can set it and check it. And there we are. So this is a good way of being able to use a desolved numeric procedure directly in an objective function for optimization. And we just look at the plot of this, but it's pretty straightforward, 0 to 2, exactly what's expected. So this is quite a toy problem. Okay, a little bit more complicated. I'm going to use the damped harmonic oscillator as an example. So this is our equation here. Mass, the damping constant, and the spring constant are all inputs, are all parameters of this equation. But we're going to look at a specific problem and say, find the value of the damping constant so that the harmonic oscillation damps as fast as possible if we're measuring the energy with 1e-6 resolution. And so that sensor would say that the oscillations would stop in the shortest amount of time. Okay. For simplicity, we're just going to set K and M to 1. You can come up with the kinetic and potential energy, which is what we're going to measure. This is our ODE that we described up there with the M and K parameters evaluated out. And now we're just going to call this desolve with this ODE, appropriate set of initial conditions, specifying the parameters. We're going to set tolerances of 1e-10 for absolute and relative error. Ask for it to be compiled, and we're going to define an event that says that when the sum of the energy is 1e-6 halt. Okay. So we call this. And just to test it, we set parameters to 1, try and integrate out to 100. And we can see that, okay, at 13.2, event 1 triggered a halt. And this was the value of time and the position and velocity at that time. And we could check it, and it'll come on as 1e-6. So again, glue code, another nice optimization procedure. I'm using this. I was sure it was documented, but I couldn't find it. So this is going to be documented in the next release, which is simply a environment variable you can use to turn this warning off. Because if you're calling this repeatedly, you don't want to see that coming up. A lot So this is otherwise quite similar to the prior optimization we had. So what do? We're taking in the parameter value. We're calling dsolve, setting that parameter value, we're computing out to 100, and we're returning, in this case, the time value, right-hand side of the first part of the result. Okay, so we can plot our optimizing procedure here between 1 and 3, and we see this. So we see that it's a bit non-trivial for the values to the left of the minimum, but it's a lot smoother on the right. This is important to look at because minimize and fsolve find local solutions. So if we actually started our solution somewhere in this region around 1.5, the value we would get would be not the minimum, but the local minimum. So to avoid this, we're calling minimize with a given range that doesn't include that minima. And we get our value. And optimize gives the objective function value and the parameter value at which that occurred. So at 1.81, we get our minimum of 6.88. Now, those familiar with this problem might know that in practical terms, the optimal value for C is for something called critical damping, where the damping occurs as rapidly as possible, is in fact 2 normally. But we see that that's not actually the minimum here because we have the additional consideration that we only need to get down to 1e minus 6, not all the way to exactly 0. So we're asking for the measurability as opposed to the precise value. And that gives us this. So are there any questions on that parameter optimization and such at this point? No? Okay. Oh, why obj? Ah, yes. Okay. Why the unevaluation quotes? Where was that? Okay, so we're using the unevaluation quotes to prevent it from attempting to evaluate at a value that isn't numeric yet. So let's see here. Where is the good? Oh, this one. This is the one with obj. Okay. Yeah, so here we ask for obj. Let's redefine this again just to be sure we've got it. If we ask for objective of x, where x isn't specified, we get an error that says that, hey, it's supposed to be numeric. By putting the unevaluation quotes around it, we say we delay evaluation. And by sending that to fsolve, we delay evaluation until fsolve chooses a value for x. So it's going to use different values of x to compute it, but it's never going to try and compute it with just x, which is going to result in the error I just showed here. Okay. All right. I'm going to move on to the next part, boundary value problems. Okay. The BVP solver. Let's look at a simple case first. This is a case with some mild boundary layers. So we have just y double prime minus 1000y is 0. Initial condition or boundary conditions, 1 at either end. Ask for the solution and look for the plot. Okay. So as I mentioned, this has some very relaxed boundary layers at either end for this DE. The larger this value here, the 1000, the tighter the boundary layers become. Okay. This is a good one. I think I briefly mentioned this yesterday in the talk, but we handle singular coefficient problems on either end. This is really handy for, especially for problems that have come from spherical or polar coordinates and are a reduction of variables. So that, because typically the radius occurs in the denominator in a lot of cases. So in this one, the Emden equation, this is coming from spherical coordinates. And this is the DE we're trying to solve, or boundary value problem we're trying to solve here. Okay. So you're going to have a problem at r equals 0, just directly evaluating this. So you need something that can actually handle that singularity. Okay. So we set our boundary conditions. The boundary condition to the left is specific value for y, and the boundary condition at the right is a 0 slope condition. Okay, so when we try and solve this directly with D-solve numeric, it complains and says that you need to use a midpoint method. This is described in the help page. So we can use one of the two available midpoint methods. In this case, I'm just going to use mid-defer and obtain a solution. And then we can look at the plot. And it looks pretty nice and smooth. You can't really tell that there's a problem at the origin. If we compare to the exact solution, we can see that we get very reasonable. And I chose these specific initial and boundary value problems because there happened to be an exact solution for those so that we could verify it. And so we see that we get very reasonable accuracy here, out to 6e minus 8. The default, I believe, for boundary value problem is 1e minus 6. We can ask for tighter tolerances, just simply specifying abs there. Unlike initial value problem integration, only absolute error is used, not relative error, for the boundary value problem solver. So you only need to specify the one. And we can look at that solution. We can see that, yeah, we get a tighter and more accurate solution with the higher tighter tolerances, as expected. Okay. All right, now, I had to look around a bit to find a really nice, challenging boundary value problem, and I found this one. There was a interesting YouTube video on this one where somebody went to all sorts of interesting links to figure out how to actually solve this problem, including flow diagrams like DE plot, if you were around for yesterday's presentation, to see, what we expect to come out. But as a problem, it's tough because we've got the leading derivative has a very, very small coefficient, and there's nonlinearity. So it's a kind of a double whammy. We have initial conditions of 1 at 0 and minus 1 at 1. And if we try to solve this directly, we have a problem. And this is the initial Newton iteration is not converging. What do I do? Like, how would I attack this? But you have to come to some, at least a mild understanding of the problem and say, okay, well, I think the main problem is this tiny coefficient here. Okay. So what would happen if we parameterized that coefficient and chose an easier value for it, like 1? And if we do, there's no problem at all solving it. Okay. What about 1/10? Same. 1/80th? Same. So we can see that, okay, so yes, smaller values of the parameter, that is the problem. Solution can easily be obtained with a larger value for that coefficient. Okay. And we can also see is as we're making that coefficient smaller and smaller, there becomes this boundary layer in the middle of the region. So now we try and go a little bit smaller, 1 over 160, and we get a complaint. And it says, well, I couldn't get the requested accuracy with a 128-point mesh, was able to get this. Consider increasing max mesh or using a larger absolute error. Okay, well, we want to keep our error tolerance the same. So we're going to bump up max mesh to, say, 512. And now we get a solution. Okay, we're not there yet because we're almost at 10. We're a little over 10% of the way there. Let's bump it all the way up to 1 over 500, and we're back to the original problem. Okay, it can't get it even with a reasonably large value of the max mesh. So how are we going to do this? This is where continuation comes in handy. Okay, continuation. I have used continuation to solve all sorts of problems. In this case, it's a case where it's a small coefficient. So it's actually just jumping out at you what value you would want to transition to get to a solution. But in many cases, you might have a nasty nonlinear ODE, and you don't necessarily know. There's nothing that jumps out at you and says, yeah, this is what you want to use continuation on. And in many cases, it's a bit of trial and error, but I've often found that small coefficients and particularly nasty nonlinear terms that can be converted to linear locally, you can do a continuation that moves from the linear to the more nonlinear problem, from a larger coefficient to a smaller coefficient. And you can actually do the two of those simultaneously with the same parameter. And I've gotten solutions out quite straightforwardly just using continuation in that way. So we're going to do a continuation here. So what I've done is I've created a value for epsilon so that when p is 0, which is where you start your continuation, you get 1. And when p is 1, which is the end of the continuation, you get the target ODE, the thing you want to solve. Okay. So we define this. We can just double check. Did we do this right? Yeah, okay. So the ODE for p equals 0 is the simple one we know is really easy to solve. And for the p equals 1 is the one we want to solve. Okay, so we try to use continuation with the 512-point mesh. And now it tells us, oh, okay, mesh size, you have too few mesh points. So increase it. And if we do, we get our solution. And you can see this is an extremely sharp interior boundary layer that we've just managed to resolve using continuation. Okay. Continuation is a very powerful tool for finding ODE solutions, but it definitely requires some degree of trial and error and human interaction to figure out what a good continuation is. Okay. So are there any questions on boundary value problem solving? Not at this time? Okay, if anybody has a question on it, or something occurs to you, you can feel free to ask it at the end and we can cover it then. Okay, something that I know is near and dear to definitely the hearts of a couple of people attending today, eigenfunction and eigenvalues. There are two basic approaches, one better than the other, usually, for eigenvalue problems. So we're going to do a simple eigenvalue problem to start, and then we're going to move on to a more complicated example second. So the first one is just to get a feel for, okay, what can we do? So the first standard eigenvalue problem, this is probably the first eigenvalue problem that people see in a course, is good old wave equation, where we have y prime plus c squared y is 0, and conditions of y is 0 on the left and y is 0 on the right. This naturally admits the 0 solution, which is very uninteresting. So there are going to be solutions for discrete values of C. And we want to try and find these. Okay. Several of you are probably familiar with shooting. Okay. So the shooting approach, we make C an unknown parameter. And we choose a value for y prime at 0 to get normalization. This is to avoid that 0 solution specifically. Okay, and we're going to search for C values that give y at 1 is 0. In other words, match our second condition here. Okay, so we define our shooting system as an initial value problem where the parameter C is free and we have 2 initial conditions. So we set this up using desolved numerical parameters. Again, we form another objective function. Okay, and we can plot the objective function to see, okay, this is C. Okay, and we see that we get a 0. Oh, I should mention. Yeah, so what this objective function is it's taking the parameter value in and giving the value at x equals 1 out. So what we're looking for here is a C value where we're getting a 0. And we can see here a little past 3, a little past 6, between 9 and 10. So we've got 3 of them that we can see right away. Okay. F-solve to the rescue. Let's find some values in the region of those approximate. And we see that we get 3 eigenvalues up front. And we can set one of these parameters to the value for the solution, and we can plot it. And we can see what we get for our eigenfunction. And in fact, we get the third eigenfunction for this problem, and we do get y at 1 is 0 as expected and required. Okay. I'm going to give, oh, I should have probably done a semicolon. Okay, so that's great. We've got an eigenvalue. Again, this is now sitting behind this wonderfully opaque desolved numeric object. What if you want something you can actually get your hands on and work with? Something that doesn't require a call to a procedure. This is another output type that's actually really handy. Let me do this one first. Another output type from desolv that's really handy, which is you can request the output in terms of a piecewise polynomial instead of a procedure. So I'm specifying essentially the shooting system with that specific value, calling the desolv numeric with that, asking for output of a piecewise over the range 0 to 1. And then I'm evaluating y of x with respect to that. What this is going to do is this is going to give us a piecewise solution. Okay, so essentially the function is equal to this piecewise, which is quite large. And we can see that we have a specific polynomial here, and it's written, of course, in Horner form to avoid round-off error for a specific range. So if we look, it's undefined for negative x, which we expect because we only asked for 0 onward. And for the first, for the first 0.005 seconds, we have this specific polynomial, which is centered at the halfway point for the Horner evaluation. And so now we get one piecewise as the output. Now, one thing that always bothered me is I never really liked piecewises because when you get the output, what if you're evaluating out here at the last point and you've got, let's say you have x just a little shy of 1. What are you going to do? Well, you're going to run through all of these comparisons that you see there before you actually reach that x equals 1. So the larger your piecewise, it's essentially the lookups are going to become linear time in the length of the piecewise, which means plotting a function would be quadratic time, which is just never a good thing. So we've got this other form, and I dare not display it, but it's piecewise binary. Okay, now what piecewise binary is it's just a version of piecewise where it's now actually broken it down into a binary nest. So the depth of the piecewise is essentially the logarithm of the log 2 of the number of branches. And the number of decisions that need to be made when evaluating any specific point is always the log of the number of branches as well. So this creates something that's a lot more uniformly evaluatable, but it's very deep and will display way off the screen. So I'm just suppressing the output for it. And we could take this binary piecewise and we just get plots for the piecewise itself, the derivative, and the second derivative. And I've just divided by these numbers so that the three individual plots come up in roughly about the same range. So we can see that I've chosen red, blue, and green. So red is the actual third eigenfunction. Blue is the derivative of that eigenfunction. And the green is the second derivative. And you can see the green is a scaled reflection of the red, which is what you expect from the differential equation we were solving in the first place. Okay, so that is the shooting method for eigenvalue problems. Now, oh, please compare execution time. All right. Omer, do you want to take yourself off mute? Did you have you used piecewise binary before? Okay, so let's do. Very hard to come up with a timing on the fly, but we'll give it a whirl. Okay, so let's see. Let's create any fun. Okay, no worries. Okay, so I'll call this eFun R and B, and we'll make the regular one not binary. That's perhaps too fast. Let's go to. All right. Okay, so there's our time of the regular evaluation. And there's the binary. It's not a huge savings, but it is a savings. So there's some overhead here. This is also a case where the actual number of cases isn't all that large because the function itself is rather smooth. So there's really, I think, only about 40 branches in this piecewise. In many problems, there can be a couple hundred, and then it makes a much bigger difference. All right, so if there are no further questions on the eigenvalues and eigenfunctions. Oh, sorry. I'm not there yet. Okay, so that was shooting. Okay. All right, so where are we? BVP approach, right? Okay. Okay, so how do we do this with a boundary value problem solver instead of an initial value problem solver? And in this case, okay, how would you do this with a boundary value problem solver? Well, one, you still need your normalization condition. Okay, and the reason you need that is, again, the zero solution is always a favorite, and you want to avoid that one. It turns out that the way of doing this with a boundary value problem solver is with an approximate initial solution. You give approximate values. Well, I should note one thing. The boundary value problem solver in Maple actually deals with parameters as a degree of freedom. So one can specify a 2-point second order boundary value problem with a free parameter and 3 conditions. And it will treat the unknown constant as something to be determined. So it's actually kind of handy that way. Great for parameter optimization applications and that type of thing as well. Okay, so we're going to choose an approximate solution of c equals 3 and y of x equals x times 1 minus x. Now, all I'm doing here is I've chosen a function that essentially is just a non-trivial arc between the start point and the end point. So I've just said, well, let's create the simplest thing, a polynomial that's just 0 at either end, which I know is my initial conditions, and some value for c. And we can ask for the value at 0. And once it's actually obtained the solution, the value at 0 is the expected thing because we've got the conditions that we asked for. But the interesting thing about this is that the value at 0, of course, gives us the parameter value directly to be able to read it off. Okay, so we can plot it. And yay, same solution we had before. No big surprise there. Okay, how are we going to get the second eigenfunction? Again, the procedure is no different, right? We're just doing the same thing. Well, we just have to pick a better value for the new c and a better value for the initial approximate solution. So like I said, there's one good way, the shooting, and there's this I call the lazy way, but I'll mention a brief advantage of the lazy way later. So now what I've done is I've said, okay, well, if we just choose an arc that goes from the start to the end, we're going to end up with the same solution as before. So instead, what we're going to do is create something that has 2 bumps in it and then say, well, give me the closest. And so we've got this as our initial approximate solution. We get a different eigenvalue. This is how you know you didn't find the same solution again. And we can look at a plot of that and we get the second eigenfunction, which is what we expect. Okay, so let's do this again. And again, third. So this is a pretty ad hoc method because you've got to come up with an initial guess of the c, and you have to come up with an initial value for the function. But the handy thing about this is this does not require you to know in advance how many prior eigenvalues there were. If you have something you know for this model is roughly about an eigenfunction, you can put that in to refine the eigenvalue that you have to get a more precise value for it. So it's a kind of a direct method of solving the problem for an instance. Okay. Okay, so this is our toy, the simple version of the eigenvalue problem. And let's get a more practical example. This comes from this example here. Comes from, again, our favorite, in this case, a polar coordinate transformation. So we end up with the denominator. So again, we're in the case where we've got one side singular coefficient, but of course, both the boundary value problem and the initial value problem solver work with this. So no problems there. Okay, and so we got the singularity and we got variable coefficients in this case. So let's try and follow the same approach. Okay, so we're going to call this, and we run into a problem. Okay, so in yesterday's talk, I briefly mentioned that symbolic analysis needs to be done to accommodate and handle singularities. That symbolic analysis that needs to be done and the checking of limits can't be done with a parameter present in the model. In order to determine the suitable values for the initial conditions for a singular model, it needs to be known in advance. So we need to make a mild modification to the approach we used before, which is instead of using a pre-existing solution and the parameter, we essentially create our shooting routine to actually do the call to desolve with the parameter value set and then do the evaluation. So this is more expensive than it was before. So we create our shooting routine to do this. And now we can look at it over a time range. Again, nice objective function form. We can see, oh, look, we've got, again, 3 crossings, 3 places where we think we have an eigenvalue. And now, again, we can get solutions for the eigenvalues in those ranges. And we see, okay, we've got 3 possible values. And we've obtained plots on the way, just not displayed them until now. And we can display what the eigenfunctions, the 3 eigenfunctions look like for this problem. Right. Okay, so BVP approach. This is, for a model like this, it's a bit more trial and error involved. Okay, so again, in this case, our BVP problem was defined with the slope at 0 being 0 and the value at 1 being 0. So our normalization condition has to be something that we haven't already specified. So for the normalization condition, and I should have mentioned this in the prior one, but our normalization, we choose y of 0 is 1. Okay, and now what we're going to do is say, okay, we want to find an approximation or initial approximation of the function. And we've got 3 boundary conditions on it. We've got these 3 here. So we're going to create approximate polynomial with 3 coefficients and essentially solve it for those coefficients. So we get these coefficients. We can evaluate the approximate solution with those coefficients, and we get this 1 minus x squared as our initial approximation. Oops. I must have assigned m someplace. Okay, yeah, I've assigned something somewhere in my prior work. Oh, no. What have I done wrong? Oh, the original problem. Thesis. Okay, yeah. Okay, m's back in there. Not sure where I assigned m, but I did it someplace. And okay, so we redefine this. Now it has m back in it. Go through the steps and we get our solution. As for the value at 1 or at 0. And we get our eigenvalue, which is essentially what we expected from the shooting technique. Okay. Okay, good. That's 1. And we can look at the plot. Okay, next, again, let's try and find the second one. And so we do so. I'm going to mention, so much like in the first case, I just added a bump, another crossing. So I set the approximate solution to a 0 at a half. So I'm just basically starting off with something that passes through another 0, get a new set of coefficients out. I'm going to make an initial guess of the eigenvalue at 10 and ask for the solution, but no, look at that. We've got the same eigenvalue back. So the function itself was not enough of a hint. So let's choose a different initial value for m and the same approximate solution. And now we get the next one. So when you get a duplicated value, you know that it's essentially just found the same eigenfunction and eigenvalue that it did before. So we want a distinct value for m. And then the third one got a little tricky. So I originally tried a crossing at 1/3 and 2/3, but that didn't work. If you look at the way the plot works, though, you can see that the crossings are not at the midpoint, but rather look kind of more to the left because the function's starting out at a positive value, going back down and back up to a 1. So the crossings should kind of be a little bit to the left side. So instead of 1/3 and 2/3, which gave me the second solution back again, I chose 1/4 and a half. And that did the trick with the third eigenfunction. So again, this is a much more ad hoc technique for eigenvalues and eigenfunctions. And the shooting method tends to work quite a bit better if you want to be systematic. Okay, so that pretty much covers the eigenvalues and eigenfunctions section. So are there any questions on that topic at this time? No? Okay. I'll move on to the DAE and delay equations section now. So a bit about the DAE solution techniques. Essentially, the two primary, or I guess three primary, core DAE solvers in Maple are prolongation projection-based extensions of RK methods. Now, prolongation is essentially just a fancy word for differentiation. It just means that you have to essentially differentiate the system and eliminate until such point as you achieve index 1, or if you're doing a full prolongation, index 0 system. But our methods that we have right now, the RKF45, CK45, and Rosenbrock methods, are capable of handling index 1 problems in general. So we only have to perform prolongation out to index 1, which means that if you send an index 1 DAE in directly, it's just solved directly. There's no symbolic manipulation required other than the standard stuff for building the procedure. But if you have a higher index problem, prolongation occurs, and this results in constraints. So we essentially create an error control mechanism to monitor the error of the constraints, and that ties into the error control mechanism for the differential step. So that we keep the error in the constraints as small as possible, and we project at the end of each step to make sure that they stay exact. Okay. So prolongation projection type techniques. There's also MEBDFI, which is a direct method. That works directly with the system without performing prolongation or projection. But we found that in general, the performance of the prolongation projection approaches is significantly better in pretty much every example. So we're sticking with that, and that's essentially what the MapleSim tool uses. It uses the D-solves prolongation projection methods, and it solves problems with thousands of equations in it. And in many cases has to perform 100, 200 steps of prolongation and projection to get an end system that it can actually use to integrate. So there's a lot of symbolics involved in the back end. Keeping the growth on that small is an interesting trick. But again, for purposes of the demonstration, we're going to start with something nice, simple, and easy to understand. The flagship, simplest index 3 DAE, which is our good old pendulum in 2D. So we have a differential equation, second order for x, for y, the Cartesian coordinate positions. And we have the constraint to say, yeah, this has to lie along a circle centered at the origin of radius 1. Okay, so pendulum. And then we have our initial conditions set up. So we declare our system, just call D solve numeric on it, and it just obtains the value, our solution directly. And as I mentioned, there's the symbolic manipulation and the projection, or I should say the prolongation occurring in the background. It sets things up for constraints. And we can look at the solution as a function of time for x. And it's like a sine, but it's a little flatter at the ends. And we can also plot, for example, the where it lives in Cartesian coordinates. And this is just showing that where we are and during the integration is we're going back and forth at the bottom of the pendulum swing here. Okay. So I'm just going to show for a simple example like this, what is projection, or sorry, what is index reduction? Because we just start out with our constraint. We differentiate once and we get a differential equation, two variables. If we differentiate again, sorry for bumping that, we get another differential equation, but we note that that differential equation has second order derivatives of x and y in it, which we can then substitute the known values from our original system in to eliminate the second order derivatives. And this can then be used to solve for or determine the value of lambda of t, which we didn't know how to do before. And that was the source of the difficulty. So we had to perform two differentiations and an elimination to get an algebraic equation in lambda. If we wanted a differential equation in lambda, we'd have to have performed 3, which means that this DAE is indexed. So this is the type of thing that goes on behind the scenes. For a model like this, it's pretty straightforward. For larger systems where there's interdependencies between the constraints, it can be far more complicated. So we can actually use this directly. We can replace the third equation, which was our constraint on x and y, with this new equation for lambda, and we can specify the constraints explicitly. And so this is just a manual way of doing exactly the same thing, and we get exactly the same solution. But the only thing to note is that for these constraints here, it may be the case that the most natural representation for them is different from just the base constraints themselves. So one might find that there's a form or combination of those constraints that can give better numerical conditioning when one attempts to work with them. This often happens in basically multi-body type formulations where the underlying constraints aren't necessarily just directly differentiated to get the acceleration. A better form of them is available. So in that case, if you have a case like that, you can use this input form directly. And that's DAEs. Are there any questions on DAEs at this time? Okay, I'll move on to delay. Okay, a basic example we had in the overview. this one. Okay. There's often, I've heard a couple of times people have said that they want to be able to specify a value that isn't just a constant as the initial condition, because as you integrate forward in time from 0, there are a whole set of values from y at -1 to y at 0 that are at this time all just being fixed to a 1. So this can be an issue, because what if your system doesn't match that? But and so this is essentially the problem statement, that we have this differential equation and we have y at negative time equals some function that's not just constant. And it's possible to represent this as a version of the same function that is constant, does use a constant initial value, but has a modifying piecewise term. Okay. And I was going to, on my list is modifying the existing code to do this transformation automatically. So it'll be handy to be able to just specify it. It's a little tricky in some cases to recognize the initial condition, because now your initial condition isn't y at 0 anymore, but it's y at negative time. So I'll have to come up with a formalism for that, but it'll be a handy thing to be able to specify this in the future. But in the meantime, one can just modify it with a piecewise to get this same effect. And we can see that the constant case, which was DSN1, and the case where we have the different value in the initial range, the DSN2, they're a bit different. So the red, where it's the time or the values at negative time are constant, give the red curve, and where we use the exponential is the blue curve. So it can make quite a difference what your initial conditions are for negative time. So the constant approximation isn't always what you want. DAE systems also support delay directly. So what we're going to do is we're going to put a lag on the term, the fictitious force term for the x and the y values. Okay. And so all I've done is define lag, and I just throw it into the equations. Okay. I'm, again, just using the simple constant assumption for the negative time. Ignore that. Okay. So we see that when we put a lag in, we no longer get true periodic behavior. And in fact, this lag has caused the behavior to change over time for the system in question. And if we look at this, we can see that, oh, okay, so we still are at least on the unit circle, which we expect because the constraint has to be satisfied. But with that lag in place, we're getting unsymmetric behavior with respect to the swinging of the pendulum. Right. So DAE support and lag and delay supported in DAEs as well. Any questions on that at this time? No? Okay. I'm going to get into the last really large part of the presentation, which is PDEs, which deserves a bit of time. So we have native support, as I mentioned, only for one space, one time PDEs, but frequently that is not the case. People have higher dimensional PDEs that they have to deal with. You can still do these in Maple. It is a bit of extra work, but I'll show an example in here of how to do that. Conservation of energy. I'm not actually sure whether the delayed pendulum has a conservation of energy property. I just mostly worked that example up to show that delay can be used with a DAE problem. And so, yeah, I'd have to play with that a little bit and try and see if does satisfy the energy conservation equation. Thank you, Heinrich, for the question. Okay, so for PDEs, okay, I'm going to start with the 1D bruslator. Okay, this is basically it's a reaction diffusion equation, and it's a nice nonlinear equation with several parameters in it that we have some good values to fix to. I'm going to set digits to 15 because some of these values are floats. So I want to lose as little precision as possible because 10's the default. And so I just represent our PDE system. Two reactants, or concentration of the two reactants is U of X and T, V of X and T. The constant concentrations of the inputs are A and B, and we have two diffusion coefficients, D1 and D2 for U and V. Okay. Now I've taken the values in the initial conditions that I'm using here in this example from this reference. You'll all have it handy in the versions of the worksheets you've downloaded if you want to check out the reference.
Alan, just a quick question.
Yes.
Here. How can you gain access to source code for delayed differential equations for research needs?
Source code. Well, the delay handling and that aspect of it is all very much built into the actual underlying methods themselves. So the only source code for handling the delayed differential equations is actually Maple, the Maple source code itself. Because what is actually happening inside, okay, so there's a lot of detail I didn't get into for delay. The trick to realize is that in fact our existing methods, which were originally implemented by Larry Champagne and Rob Corliss, the RKF45 and the Rosenbrock methods, they essentially have a built-in interpolant that is guaranteed accurate within the solution accuracy. Now, this interpolant can be retained and stored for any period of time prior. And so really, the handling of the delay and that type of thing is really a complex way of storing the interpolant value from prior times only back as far as you're absolutely sure you need it, because it takes memory. And so the trick in delay, implementation of delay, is to have something that has a built-in interpolant and have the ability to store prior data. Skip Thompson is also a approach. Okay, so the short answer is that we don't really have accessible source code for delay differential equations for research. Okay, but you can directly put your delay problem into dsolve and set compile to true, and it will run in compiled code. Okay, so back to the bruslator. So as I was mentioning, there's this reference. The reference I mostly use for the values to give suitable and reasonable values for the initial and boundary conditions, which is trickier than you might expect. So we get this set of initial and boundary conditions, this set of PDEs. We can obtain the solution numerically, again with PD solved numeric in this case instead of desolved numeric, because these are PDEs. And we can plot the concentrations U and XT, V, XT at a specific time value as a function of X. And we can see that the U at T equals 1 is a nice symmetric, almost symmetric thing. And V, not so much. I believe that's U and V. So we can look at a 3D plot of U and of V. So we can see as time goes forward, this is the profile of the solution. in 3D. This shows an example. So I'm doing a plot of, in this case, the concentration U at a specific x value, at a point in the domain as a function of time. So you can see essentially how the value at that specific point is evolving, and you can see it's kind of asymptoting out to a about 0.6, which is what we expect because that is the equilibrium, or that's the constant concentration for U. The constant concentration for B is 0.2. So we expect it to asymptote out to a value of 6. But what is interesting here is it actually does not asymptote smoothly out to 6. It actually goes under. So what we can do is see here that as time goes on, we're looking at the difference between the value of U and the constant concentration at 0.5 for time from 0 to 30. And we can see that for the first 6 seconds, it's above, but it actually drops slightly below and then goes above again. So one would think, from purposes of reaction diffusion, we wouldn't think that there would be kind of this type of going past and back like a reaction. And we can look at a 3D plot in that region, and we can see, yes, it does drop below, but it doesn't drop very far below before coming back up. So this might be a situation where what we might say is, well, maybe we kind of want to look at our model. Maybe we've made too many assumptions. Maybe there needs to be an additional term in the modeling. Okay. Are there any questions on the Breslator?
There's a question from
Oh,
Samir.
yes.
Is PD solve numeric the Maple based on method of lines, converting PD to set of ODEs and using dsolve numeric to integrate the set of ODEs?
No, it is not. The PD solve numeric in Maple is actually a full discretization of finite difference technique that's implemented. It's not using method of lines, but I'm about to use method of lines. So thank you for the fantastic segue. But yes, the 1D case is using a discretization and finite differences. So, but the 2D heat equation, on the other hand, is going to be using the method of lines. Okay, so we don't have native support for 2D. One of the difficulties with this is that unless you have a very restrictive set of domains, or unless you have something that's a crazy geometry package, it's a difficult thing to do. If you restrict to 2D PDE solutions over a rectangular domain, it's a lot more straightforward, but often problems of interest will include edges, may have a semicircular part. There's all kinds of complexities associated with doing the 2D problem in general. So there is an approach one can use with a good bit of work on your end to do this, but it will allow you to use exactly what Samir mentioned, which was the PD solve or using method of lines and the ODE solver to solve a 2D or a 3D problem in Maple. And so I'm actually going to solve here the 2D heat equation in Maple using method of lines. So this is the PD in question. It's pretty straightforward. Standard heat equation, first derivative of U of X, Y, and T with respect to time is equal to the diffusion constant times essentially the sum of the second derivatives of the concentration or the heat. And our boundary conditions, we're going to pick the simple ones, which are that all along the boundary, we've got 0. Okay. So how are we going to set this up? And one of the reasons I just wanted this worksheet distributed out is this can actually be used as a starting point for all kinds of other PDE problems. One can change the conditions. One can change the differential equation and play with this and use it as kind of a starting point for doing PDE solutions in 2D using method of lines. So our initial condition, I don't know what it is yet, so I've just set it to f of xy. What are we going to do? We're essentially going to do the method of lines. The first thing we actually need to do is convert our spatial coordinates into a discrete grid. Okay, and we're going to do that using finite differencing. Okay, and we're going to do a finite difference grid n+1 by n+1 over 0 to 1, 0 to 1. So the first thing we need to know is our basic single variable finite difference formula, which is this one here for a second order derivative. Okay, and this is a well-known formula. It's available in a lot of places. There's a simple one for the first order derivative as well, but what this can actually be derived from basic principles in Taylor series as well, quite easily. Higher order derivatives as well, but you'll need more points. So I'm going to choose 20 points. So this is going to be a 21 by 21 problem with a total of a little over 400 unknowns, but we'll actually end up with a little less in a sec because the boundary conditions fix values. So now our discrete PDE is obtained by this discretization to say, well, we have a bunch of U's on an IJ grid. So the derivative of Uij as a function of t is given by the diffusion coefficient times the finite difference in the x direction plus the finite difference in the y direction for the second order derivatives, using this formula right here. Right? So we get this rather simple equation out. Well, it's just basic math, unfortunately. It's a differential equation where the left-hand side depends on 5 different unknowns on the right. And this will be for the current value at the current point and one node direction in every direction, the 4 directions. Our boundary conditions, we have to also turn those into discrete form. And we do that here. And this just basically says that the value of U0j for all j's is a 0. For U20j for all j's is a 0. UI0 for all i's, and so on. So this is just setting your boundary to 0, your boundary unknowns directly to a 0. So we form a set of all the boundary conditions for the problem, which is a fairly big one. You're going to see a lot of colons here that we don't want to display. We're going to form all of the PDEs into a set and combine the boundary conditions. I'm going to choose this as our initial profile. All kinds of options are available, but this is, once again, the nice simple case where, yeah, it satisfies the condition on all the boundaries, and it's a non-trivial. So we build our ICs for all I and j. And you'll notice that I'm looping only from 1 to n-1 because the 0 and the n points are known, fixed. And we just throw this mess into desolve numeric, and we can get a solution out, which is extremely helpful. It's just a bunch of numbers, right? I mean, what are you going to do with this? So what we want is we need a way of turning this into something we actually want to look at. So I'm going to create a matrix here. And this matrix is quite simply just the values on the grid. And I've simplified it by setting the boundary condition values in advance. So I got my M. Now, those of you who attended Dave's talk yesterday will recognize the plot 3D and grid hacks that I've got in here. These are just direct access to the 3D plot structure. And what we're going to do is form a 3D plot directly from the combination of this matrix and the call to desolve, and create something as simple and as short as this to actually build a plot and display it at a specific solution value. And there we have it. So it's just simply calling this routine will give you a 3D plot of the solution at the initial value here. Bahia, yes, by all means it is. Is possible. Okay, so the question is it possible to do something for X, Y, Z, and T? And yes, you just have to come up with a larger discretization, and it'll be in 3 dimensions and have 3 times as many, or and have exponentially more variables. So for a 20 by 20 by 20 problem, you're going to have 20 cubed equations to deal with. So this can be expensive, but I'm going to get to something at the very last thing I'm going to cover is going to give a couple of hints on how to do this even better. Okay. But this is just the direct approach for this. And in terms of working with equations. So we get our 3D plot here. Oh, wait, we've got another late professor. Okay, wrote more than 15 books on MOL for solving PDEs, code available in Maple, MATLAB, Fortran, R. Okay, so apparently Samir has posted a link to some code for method of lines in Maple, and I will definitely be looking into that. But yeah, this is what I just wanted to more show here is you can do this directly with DSelf if you need to go to a higher dimension. And you can do 3 as well. But I'd be curious to see whether Dr. Scheisser wrote or is using DSolve under the hood. I'll have to check. But anyway, so this is our plot of our solution at 0. If we look at our initial condition at 0, yeah, okay, good, it matches. So at least we've done that right. We can ask for a solution out at t equals 0.25, and we can see that it's very similar to the solution at 0, but it is dropping in height. So directly animate as well. And there we are. Okay, so there is a question or a statement in the chat. Does it matter if a for loop is used instead of seek to create an array of equations or boundary conditions? I'm going to say yes, because if you will get the same effect at the end, but there's an efficiency aspect, especially if you're dealing with large things. So in a for loop, what are you going to do? You're going to build a set of equations by adding one in at a time. So you're going to be changing a data structure of length 1 by adding 1 to it, and then 2 by adding another, and 3 by adding another. Every one of these intermediate data structures takes memory and takes time in Maple. Seek is very smart in that what seek does is it does not form an intermediate data structure. It just forms the end data structure. So when you do a seek to, 400, it will do that once. If you do a for loop and append 400 things, your expense is essentially quadratic in the length of the loop. So yes, whenever possible, use seek instead of for. I think that was covered in Paul's tips and tricks for efficiency in Maple from last conference last year, 2024, I believe. But yes, whenever you can, use seek for an advocate of seek. Okay, so this is a way of doing PDEs in Maple directly. even if one doesn't want to do it this way, this is a good way to demonstrate to potentially a student how to use method lines, how this type of thing works. But this is a good way of getting a solution. And what is particularly handy is the ease at which you can actually build a plot. Again, knowledge of these plot primitives is a really good thing, and you can't plug that enough. So, okay, on to my last topic, and which is good because I think I only have 9 minutes left. Is that right, Kash?
That's right. Please leave a minute
Okay.
for questions.
Yeah, I will. Well, this is actually a really straightforward thing. So I'm just gonna, okay, so we have a programmer interface for DSolve. This is described in detail in the help. So if we have a model like this and we try to essentially form it as a system, we have to, the problem is this int is going to prevent you from being able to do the DSolve directly. So this is a case where you kind of need to use the procedure form. Okay, there is a procedure form available for DSolve, and it allows you to specify basically the problem as a vector of first order differential equations. So you have to convert the system to first order. And then you create an evaluation procedure, and that evaluation procedure can call anything. Okay. Now, thing to keep in mind is that if it calls something particularly complicated, compile does not work. But it can call anything you like from within Maple. And you can then obtain a solution and compute it. And in this case, what's actually happened under the hood is this has done a whole whack of calls to int for various values of the t value for this integral. So it's essentially calling back into Maple's int, of LF int, to obtain this solution. Now, this might seem a little bit fictitious, and sometimes procedure forms are hard to use, but looking back at the PDE for method of lines, instead of writing a whole whack of equations, wouldn't it be better to just put that in a loop and have a really, really simple procedure that essentially just loops through and computes all the different values on the grid? Now your procedure, instead of being a monster, looks actually quite small, and it's really efficient to work with it and set up initial conditions. So the procedure form can, and the programmer interface can be really handy thing.